Problem number 1. According to a report published by Gallup Institute on February the 20th, 2020, based on the interview that took place between February the 3rd and February the 16th, 77% of 1,028 randomly selected American adults felt they were generally confident in the federal government's ability to handle a potential coronavirus outbreak. Find the 98% confidence interval. Now, in retrospect, this percentage, 77%, looks ridiculously high, but please understand that this interview took place in early February, and at the time, people still did not understand the severity of the problem and also the utter incompetence of Trump administration. And of course, the figure, the confidence figure went down and down all the way over to the presidential election. Everybody knows that. But this is a math course, so please just focus upon the mathematics of the problem. We're going to take 77% for granted based upon the sample size n equals to 1028. Okay, here we go. Let's find the 98% confidence interval. First, is it going to be t-curve or z-curve? Clearly, this is going to be a z-curve. Sample size is too big. And greater than 100 is usually the best criterion these days. Some textbook authors use a century-old criterion of greater than 30 or not, but come on, this is so 20th century. Nowadays, we have much better computing tools, so 100 or bigger, then we use z-curve, and less than 100, we usually go for t-curve. But in this particular case, there's another reason. This is about proportion, so t-curve does not apply. Okay, in any case, here's the outline. 98% in the middle, so we need 2% shared by the left and the right. So 1% here to the left, 1% here to the right. In the center, we have 77%. We're going to find out this value x1 and x2. How do we do that? Same formula, z-score is n minus center over SE. Let me expand the font a little bit. And this is going to be, and I don't know that. Center 0.77 because we are starting from the 77%. And then SC, what is this? Square root of observed probability. 1 minus of that. Observed probability here is 0.77. 1 minus of that. And divided by 1028, the sample size. 77% and 1028. Is everybody comfortable with this SE computation? P, 1 minus P, over square root of n. Actually over n and total quantity square root. And this is equal to the z-score associated to, I'm looking for the left-hand side, this one. So associated to 1%. Excuse me. In the previous exercise set, I used the left-hand side all the time. So this time, let me choose the right-hand side. Let's look for x2 instead of x1 first. I could do that. In that case, we have 98% here, 1% there. So we have to look up 99%. 98 there, 91% there. So 99% total. In any case, let's look for x2 first. So this is going to be positive of And here's the Z table. Let's look up 99%. Here we go. 2.33. That's the closest, isn't it? 2.33. 2.33. And this is the quantity you're looking for. Okay, let's solve this equation. Flip this denominator to the other side. Times 0.77, 0.2723 over 1028. Sorry about that, wrong key. X2 is therefore approximately equal to 0.77 plus 2.33 times this quantity here after flipping around. And that is equivalent to, let's do this computation. And this is what we get. 0.800 something, so about 80%. And that's for X2. How about X1 here? You can go back and look up the table for 1%, but I don't want to do that. Let me use the symmetry. I'm going from here to the left, so I'll have to make a change to negative here, and this computation here will become 0.3794. Looks like I'm getting approximately 74%. And that's the conclusion. 74% to 80%, approximately speaking. And here's a little bit more accurate computation using a little bit more accurate Z-score figure. Oops. Okay, sorry, I just corrected a typo. Negative 2.325 expressed a little bit more precisely speaking, instead of negative 2.33. 2.6 as a matter of fact, not 2.5. Anyway, okay. A little bit more accurate computation. It should be 2.6, not 2.5, but I don't care. I mean, everything is approximation anyway, and then even more crude computation gave me something this good, so why would I bother? Anyway, the key here is to look up this Z-score formula, use the Z-score formula associated to SC equals to the square root of P1 minus P over N. Whenever you have proportion, that's something you should do associated to the Z table. And of course, that works only when N is bigger than 100, ideally. But for proportional problem, if you have N value less than 100, then the chances this entire sample study is going to be tossed out. So you won't have to worry too much about those kind of things. Here's the next problem here. This time we have a mean, not proportion. So this thing is going to be a little bit different. Now we have, okay, let's go ahead with the problem. In 1995, Cook County, Illinois conducted a study to determine how far the head of household travels to work. A simple random sample of 2,518 households was chosen and occupants were interviewed. The survey found the mean commuting time for households was 42.6 minutes and the standard deviation was 16.7 minutes. And then the sample size is humongous, 2,500 something, way bigger than 100. So explain which distribution is better, T or Z. sample size is large. 2518 is way bigger than 100. And as I told you before, some people use 30 here, but that's so old. Nowadays, 30 is not considered good enough. Okay. Next, estimate the 95% confidence interval. Well, here's the initial picture, and I think everybody can visualize this easily now. 95% in the middle, 2.5 there, 2.5% there. How about solution? End minus center over SE is the formula there, and then that's approximately equal to, let's see, x1 minus 42.6 over standard deviation of 16.7 over square root of what's the sample size? 2518. Okay, that's approximately equal to negative 1.94. I think negative 1.96, excuse me, I forgot. Let me look up. So where is 2.5%? Okay, that's negative 1.96. So negative 1.96, that's for the left-hand side endpoint. And let's find it out. x1 minus 42.6 is approximately equal to negative 1.96 times 16.7 over square root of 2518. And then if I flip this to the other side as well, then we have 42.6 like this. And then that's approximately equal to, okay, from now on I have to use calculator, and you can punch it to calculator, but I want to save time. This is what we get, 41.9477. That's the left-hand side endpoint here. Now, how do I find the right-hand side endpoint? I can repeat the process, yes, but what's the point? Let's use the symmetry. From here, let's go to the right. So this changes to plus. And consequently, we have to do this new computation. And I get 43 point something. There you go. There goes my confidence interval. 41.9477 to 43.24523, like this. There goes the 95% confidence interval, and this is the lower bound of the confidence interval, and this is the upper bound of the confidence interval. Here's a little bit more accurate computation. Now we talked about confidence interval and lower bound and upper bound of the confidence interval. How about upper confidence bound? That's a little bit different. Not the confidence interval. Even the initial picture differs. Only here I have 5%, and this one goes all the way to negative infinity. How about the computation? N minus N2 over SC, or this computation. X minus 42 minus 6 over SC is 1.645. Associate this to this red part, 5% to the right. And then do your computation solving for X. This is what you get. And that is the upper confidence bound. So 95% upper confidence bound is not the same as the upper bound of 95% confidence interval. They're different.